On April 8, 1941, at precisely 2:35 p.m., a massive aircraft took to the skies from Nakajima's test facility just outside Tokyo. This aircraft was no ordinary plane, it was an impressive engineering feat, measuring over 100 feet in length with a wingspan stretching nearly 140 feet. As the four powerful engines roared to life, the engineers from the Imperial Japanese Navy watched with bated breath. They had invested 18 months into the construction of this strategic bomber, pouring $950,000 into the project, which was based on an American airliner that had been rejected by the U.S. market. To conceal their true intentions, the Japanese had even staged a crash, creating a facade to hide their espionage efforts. Now, as the aircraft lifted into the humid air, the pilot pushed the throttles forward, but something was amiss. The aircraft climbed slowly, struggling against its own weight, and the controls felt unresponsive. This moment marked the culmination of a project that had begun with the theft and reverse engineering of American technology, aiming to create a strategic bomber capable of striking targets across the Pacific. Instead, they had inadvertently constructed one of the worst heavy bombers in aviation history, a testament to the perils of engineering hubris and the assumption that imitation equates to understanding. This narrative unfolds not during a time of war, but rather during the golden age of American commercial aviation in the 1930s, a period characterized by rapid advancements and fierce competition among aircraft manufacturers. The story of how Japan acquired America's rejected airliner and transformed it into a spectacular failure is one of espionage, deception, and the stark realization that copying someone else's work is not the same as comprehending it. The year was 1935, and commercial aviation was undergoing a transformative phase in America. Airlines were expanding their routes, and passengers were becoming increasingly confident in air travel. Aircraft manufacturers were fiercely competing to build the next generation of airliners, each striving to outdo the other in innovation and performance. The Douglas Aircraft Company had recently introduced the DC-3, which would go on to become the most successful commercial aircraft of its era. Even before the DC-3 entered service, airlines were dreaming of even larger and more capable aircraft. William Patterson, the president of United Airlines, approached Douglas with an audacious vision. He envisioned a four-engine airliner that could cross the entire continent without stopping for fuel, capable of carrying 42 passengers in daylight service or 30 in sleeper berths for overnight transcontinental flights. This aircraft would feature pressurized cabins, allowing passengers to fly above the weather, and come equipped with air conditioning for added comfort. It represented the cutting edge of aviation technology. However, the proposal was fraught with challenges. No airline had ever operated a four-engine land plane for commercial passenger service, and the technology Patterson described barely existed. Building such an aircraft would require solving complex engineering problems that had never been tackled before, with enormous risks and staggering costs involved. Yet, the potential rewards were equally impressive. Whoever built the first successful four-engine airliner would dominate the commercial aviation market for generations. Douglas was intrigued by Patterson's vision but remained cautious. They understood that the challenge would stretch their capabilities to the limit. They agreed to proceed only when other airlines expressed interest in the project. American Airlines quickly joined the endeavor, followed by Eastern Airlines. Pan American Airways and Transcontinental and Western Air, which would later become Trans World Airlines, also committed to the project. Each airline contributed $100,000 toward development costs, creating a $500,000 fund to support what would become the most ambitious commercial aircraft ever attempted. The engineering challenge of developing the DC-4 was immense. Douglas assembled a team of some of their best designers, led by Arthur Raymond, who had previously led the DC-3 program. The team faced unprecedented problems: how to build a wing strong enough to support four large engines while remaining light enough for efficient flight, how to design landing gear capable of handling an aircraft weighing over 60,000 pounds, and how to route fuel lines, hydraulic systems, and electrical wiring through a fuselage that had to accommodate passengers comfortably. As work progressed, the questions multiplied. How could they pressurize a cabin at high altitude without creating structural stress that would lead to metal fatigue? How could they provide enough auxiliary power to run air conditioning, cabin lighting, and galley equipment without overloading the electrical system. Furthermore, how would they train pilots to fly an aircraft that was twice as heavy and complex as anything they had operated before? Over the course of 2 years, the team produced an astounding 8,100 drawings documenting every aspect of the aircraft. They built a detailed wind tunnel model and conducted 866 separate tests, totaling over 1,100 hours of research. They studied airflow patterns, stability characteristics, and control effectiveness at speeds and altitudes that no previous airliner had achieved. The engineering effort was monumental, utilizing 1,300,000 rivets to assemble the prototype and measuring a total of 500,000 man-hours, an unprecedented investment for a commercial aircraft. What emerged from this exhaustive process was the DC4, an aircraft that was unlike anything the world had seen before. It was a marvel of innovation from nose to tail, featuring the first large aircraft with tricycle landing gear, which allowed it to sit level on the ground rather than tilting back on a tail wheel. This seemingly simple change had profound implications for passenger boarding and cargo loading, making ground handling much more predictable. The DC4 was designed with several groundbreaking features that set it apart from its predecessors. The wing was massive, spanning over 138 feet from tip to tip, necessary to generate enough lift to carry the aircraft's weight while maintaining acceptable landing and takeoff speeds. The wing design borrowed from the proven DC-3 but was dramatically scaled up to accommodate the new specifications. For Pratt & Whitney, our 2180 Twin Hornet engines were mounted on the wings, each producing 1,450 horsepower. The engines were positioned with noticeable toe, meaning they were angled slightly outward rather than pointing straight ahead. This unusual arrangement was designed to improve stability by creating favorable yaw moments during single-engine operation, enhancing safety and control. One of the most distinctive features of the DC-4 was its tail design. Instead of a single vertical stabilizer like most aircraft, the DC-4 had 3 vertical fins, one in the center and one at each end of the horizontal stabilizer. This configuration was chosen for practical reasons. The aircraft was so large that a conventional tail would have made it too tall to fit inside existing hangars at airports across the country. Airlines could not afford to build new hangars at every destination, so the triple tail kept the overall height manageable while providing adequate directional control. Inside the fuselage, the DC-4 was designed for a level of luxury that commercial passengers had never experienced. The cabin was wider than any previous airliner, allowing for more comfortable seating arrangements. Passengers sat in chairs that resembled actual furniture rather than the utilitarian benches of earlier aircraft. The aircraft could carry 42 passengers in a standard configuration, and Douglas also developed sleeper variants with fold-out berths for overnight flights, allowing passengers to board in New York, eat dinner, sleep in a bed, and wake up in Los Angeles. Air conditioning kept the cabin comfortable regardless of outside temperatures, and provisions for cabin pressurization were included, though this system was not installed in the prototype. The flight deck was equally advanced, featuring power-boosted flight controls that reduced the physical effort required to fly the large aircraft. Without power assist, the control forces would have been so heavy that pilots could not have maintained precision during landing or maneuvering. On June 7, 1938, the DC-4 prototype was ready for its first flight at Cloverfield in Santa Monica, California, where Douglas had its main factory. Carl Ananson Cover, Douglas's chief test pilot and one of the most respected aviators in America, was at the controls. Cover's remarkable career mirrored the development of modern commercial aviation. He had learned to fly in the Army during World War I and joined Douglas in 1930. Cover meticulously ran through his pre-flight checks, knowing that thorough preparation could prevent deadly surprises. One by one, he started the 4 engines, each Twin Hornet coming to life with a distinctive rumble. The aircraft, registered as NX-1810 with construction number 1601, rolled toward the runway, and the ground crew watched with a mixture of pride and anxiety as 2 years of their work were about to be tested. As Cover advanced the throttles, the heavy DC-4 began to accelerate down the runway. It used a significant amount of runway before reaching flying speed. At the proper airspeed, Cover pulled back on the control column, and the aircraft lifted into the California sky. The first successful flight lasted about 45 minutes and went without incident. Cover reported that the aircraft handled reasonably well, though there were certain characteristics that would require further investigation. Testing continued throughout the summer and fall of 1938, with Douglas pilots evaluating the aircraft's handling characteristics at various speeds and altitudes. They tested its performance in climbs, descents, and turns, examining the reliability of its complex systems under the stress of repeated operations. However, problems emerged, as they always do with new aircraft. Some systems did not work as designed, and some performance numbers fell short of predictions. Consequently, the type certificate was delayed while issues were addressed. On May 5, 1939, the Civil Aeronautics Authority finally granted approval, and the DC4 was officially certified for commercial operation. The prototype was then turned over to United Airlines for in-service evaluation. This moment marked a crucial turning point, determining whether the DC4 would be a breakthrough or a disappointment in commercial aviation. The evaluation by United Airlines revealed serious issues that threatened the entire program. Despite the successful test flights and the presence of aviation's founding father, Orville Wright, who had flown on the DC4 during its demonstration, the aircraft was deemed too complex for practical airline operation. Its sophisticated systems required specialized maintenance that most airports could not provide. Mechanics trained on the simpler DC-3 were baffled by the DC-4's intricate electrical systems, hydraulic circuits, and control mechanisms. Operating costs were significantly higher than projected due to the time and expertise required to keep the aircraft flying. Additionally, the DC-4 consumed fuel at alarming rates. The four engines drank gasoline faster than anyone had predicted, leading to a range that fell short of expectations. As the evaluation continued, the aircraft's performance numbers were scrutinized, especially after the seating capacity was increased from 42 to 52 passengers to improve economics. This change pushed the gross weight up to 65,000 pounds, far above the original design weight. The fundamental problem was weight. The DC-4 had grown heavier throughout development as engineers added systems and strengthened structures to address issues that emerged during testing. Every solution seemed to add more weight, resulting in engines that struggled to carry the increased load. The climb performance was poor, cruise speed disappointing, and range insufficient for the transcontinental missions the aircraft was intended to fly. One by one, the sponsoring airlines delivered their verdicts. Pan American and Transcontinental and Western Air had already withdrawn from the program before the first flight, choosing instead to invest in the Boeing 307 Straightliner, which, although smaller and less ambitious, actually worked. Now, United, American, and Eastern Airlines reached the same conclusion. The DC-4 was impressive technology, but it was not suitable for commercial service. Faced with the prospect of an embarrassing and expensive failure, Douglas executives had to decide what to do with their white elephant. After investing years of work and approximately $3 million of their own money into an aircraft that no one wanted to buy, they opted for a two-part strategy. First, they would go back to the drawing board and design a new four-engine airliner based on the lessons learned from the DC-4 failure. This new aircraft would be simpler, lighter, and more practical, utilizing proven Pratt & Whitney R2000 engines instead of the troublesome Twin Hornets. Secondly, Douglas would attempt to sell the original prototype to recover at least some of their development costs. Finding a buyer for a rejected airliner would not be easy, as anyone with the technical sophistication to use such an aircraft would likely be aware of its problems. However, the alternative, scrapping the prototype and writing off the entire investment, was not appealing. In late 1939, representatives from Japan's Mitsui Trading Company approached Douglas with a proposal to purchase the DC-4 prototype for use by Japan Airlines, known in Japanese as the Nippon Koku. The airline was expanding rapidly as Japan's empire grew, and they needed modern aircraft to serve routes across Asia and the Pacific. Despite its issues in American service, the DC-4 represented technology far ahead of anything available in Japan. Douglas saw an opportunity to cut their losses, as the Japanese were offering $950,000, a substantial sum that would offset some of the development costs. The transaction appeared straightforward to Douglas executives. A foreign airline was purchasing an American commercial aircraft for civilian use. There was nothing illegal or unusual about it, as American manufacturers regularly sold aircraft to foreign customers. Export controls on commercial aircraft were minimal, and Douglas saw no reason to refuse the sale. However, what Douglas did not know, and what the American government was unaware of, was that Japan Airlines was not the real buyer. The airline was serving as a front for the Imperial Japanese Navy. The Navy had been closely monitoring American aviation developments for years, particularly interested in four-engine aircraft. Japan's aircraft industry had achieved remarkable success with single-engine fighters like the Zero and twin-engine bombers like the G4M Betty, but they had never attempted a four-engine design. The engineering challenges were simply beyond Japanese experience. A true strategic bomber capable of crossing the Pacific Ocean required four engines, as the distances involved were too great for twin-engine aircraft to cover while carrying useful bomb loads. American B-17 bombers had demonstrated the capabilities of four-engine aircraft, and the Imperial Japanese Navy sought to acquire that capability for themselves. They dreamed of being able to strike American bases across the Pacific, even envisioning bombing Hawaii or the continental United States. However, Japanese engineers lacked the know-how to build such an aircraft. The DC4 offered a solution that seemed almost too good to be true. Here was the most advanced four-engine aircraft in the world, available for purchase through normal commercial channels. The Japanese believed they could improve upon the design with their own engines and modifications. They planned to buy the aircraft, study its construction, learn its secrets, and apply that knowledge to build their own bomber. The Imperial Japanese Navy approved the plan and arranged financing through Mitsui Trading Company, with Japan Airlines serving as the public face of the transaction. On September 29, 1939, workers at the Douglas factory in Long Beach, California, disassembled the DC-4 prototype and loaded it onto a freighter bound for Japan. The aircraft was carefully packed in crates, with Douglas providing all of the engineering data files accumulated during development, including drawings, specifications, test results, performance data, and maintenance manuals. Everything Douglas knew about the DC-4 went into those crates. A team of Douglas technicians traveled to Japan to help reassemble the aircraft. They arrived at Haneda Airport near Tokyo in early 1940 and began setting up the aircraft for flight. Japanese engineers observed every step with intense interest, asking questions about assembly procedures, the purpose of various components, and the design choices made by Douglas. The Americans believed they were providing normal customer support, unaware that they were teaching potential enemies how to build strategic bombers. Once the reassembly was complete, the DC-4 was painted in the emerald green and silver livery of Japan Airlines. It became the largest and most advanced aircraft in Japan, garnering attention from newspaper reporters and airline executives. However, despite the grand announcements of its impending service on prestigious routes, the DC-4 never carried a single paying passenger for Japan Airlines. Almost immediately after reassembly, and following a few initial test flights to verify the aircraft's functionality, it was quietly transferred to Nakajima Aircraft Company under the Navy's direction. Nakajima had received a contract to develop a long-range heavy bomber designated the Experimental Type 13 attack bomber, with specifications calling for an aircraft capable of a minimum range of 3,000 nautical miles, sufficient to reach targets across the vast Pacific Ocean. The DC-4 would serve as their starting point. To explain the sudden disappearance of Japan Airlines' flagship aircraft from public view, the Japanese government fabricated a cover story worthy of a spy novel. In mid-1940, Japanese press outlets reported that the DC-4 had crashed into Tokyo Bay shortly after takeoff from Haneda, claiming that the aircraft was lost and nothing had been recovered from the water. This fictional narrative served multiple purposes. It explained the aircraft's absence, prevented American intelligence from tracking its fate, provided cover for the Navy's secret bomber program, and discouraged any awkward questions about the disappearance of a brand new airliner. At Nakajima, engineers went to work with intense focus. They meticulously measured every dimension of the DC4, analyzed its structures and systems, weighed individual components, traced wiring harnesses, and created detailed drawings of parts designed by Douglas. They photographed everything from multiple angles, essentially reverse engineering the aircraft down to its smallest details. What emerged from this study was the Nakajima G5N, which the Navy designated as the experimental Type 13 attack bomber. Nakajima named the aircraft Shinsen, meaning deep mountain, in Japanese, evoking images of strength and permanence. The Japanese hoped their new bomber would embody these qualities when it flew against American targets. The G5N borrowed heavily from the DC4, with the wing being essentially identical in platform, structure, and engine placement. The tricycle landing gear was copied directly, providing the same ground handling advantages as its American ancestor. The overall size and configuration closely followed the DC4, but the fuselage was completely redesigned for military purposes. Instead of a passenger cabin, the G5N featured a long ventral bomb bay capable of carrying up to 4,000 kilograms, approximately 8,800 pounds, of bombs or 2 aerial torpedoes for anti-shipping strikes. The bomb bay was designed for flexibility, allowing crews to configure weapon loads based on mission requirements. The nose was reshaped with a glazed compartment for the bombardier, providing visibility for aiming weapons. The cockpit was positioned higher and further back than on the DC4, and defensive armament was installed in multiple positions. Two 20mm Type 99 cannons provided heavy firepower, one in a powered dorsal turret and another in a tail turret. Four 7.7mm Type 92 machine guns added lighter defensive capability in the nose, ventral, and waist positions. The distinctive triple tail of the DC4 was replaced with a twin fin arrangement, which was more conventional and easier to manufacture with Japanese tooling. The fabric-covered control surfaces followed standard Japanese aircraft practice, and the G5N was designed for a crew of 7 to 10 men, depending on the mission configuration. For power, Nakajima chose their own NK-7A Memori engines instead of attempting to copy the American Pratt & Whitney design. The Memori was an ambitious power plant, a 14-cylinder air-cooled radial that the Smithsonian later described as the most powerful 14-cylinder engine ever built. Each Memori was supposed to produce 1,870 horsepower, a significant improvement over the 1,450 horsepower produced by the Pratt & Whitney twin Hornet engines in the original DC4. Japanese engineers believed that more powerful engines would compensate for the additional weight of military equipment. However, only about 200 Memori engines were manufactured between 1941 and 1944, reflecting the difficulties in producing such an advanced design. The first G5N prototype was completed in early 1941, and it was an impressive sight sitting on the ramp at Nakajima's test facility. Over 100 feet long with a wingspan of nearly 140 feet, it dwarfed every other aircraft Japan had ever built. Navy officials inspected their new bomber with pride, believing Japan was finally entering the era of four-engine strategic aviation. On April 8, 1941, at 2:35 p.m., the first prototype took off on its maiden flight, with Imperial Japanese Navy observers watching anxiously as the massive aircraft climbed away from the airfield. However, the test pilot's reports shattered that dream. The G5N was heavy, even heavier than expected, and the Memori engines were not delivering their promised power. The theoretical 1,870 horsepower rarely materialized in practice, with the engines running rough and requiring constant adjustments. They overheated during sustained climbs, and their reliability was poor, leading to frequent failures that grounded the aircraft for repairs. The flight controls felt sluggish and unresponsive compared to smaller Japanese aircraft. The G5N did not handle like a fighter or even like the twin-engine Betty bomber, it handled like what it was, an overweight converted airliner straining against the limits of its design. Performance numbers confirmed the pilot's assessments. The maximum speed was only 261 miles per hour at optimal altitude, far slower than contemporary American or British heavy bombers. The American B-17 could cruise faster than the G5N's maximum speed, while the British Lancaster and Halifax bombers were both faster and could carry heavier bomb loads. The service ceiling was just under 25,000 feet, limiting the aircraft's ability to fly above enemy fighters and anti-aircraft fire. Climb rate was poor, requiring extended time to reach operating altitude, and most critically, the range fell short of requirements. The G5N could fly about 2,600 miles, well under the 3,000 nautical mile minimum specified by the Navy. The Navy had requested a bomber capable of striking targets across the vast Pacific Ocean, but what they received was an aircraft that could barely reach the nearest enemy bases, rendering it vulnerable to interception throughout its mission. The dream of bombing Pearl Harbor or striking the American mainland was clearly impossible with the G5N. The aircraft simply could not fly that far while carrying weapons. In response to the disappointing performance, Nakajima built additional prototypes, hoping that refinements and adjustments would resolve the issues. The second prototype flew, but despite engineers modifying engine cowlings, adjusting propeller pitch settings, and tweaking the fuel system, performance improved only slightly, remaining far short of requirements. A third prototype incorporated further changes, and then a fourth was built. Each aircraft exhibited the same fundamental flaws, with the Momori engines continuing to cause problems. They overheated during climbs, vibrated excessively at certain power settings, and failed at inconvenient moments during test flights. Nakajima engineers were forced to detune the engines to improve reliability. Running the Momori at lower power settings reduced mechanical stress and decreased failure rates, but it also reduced the already inadequate power output. The performance problems became even worse, putting the G5N in a vicious circle. The engines could not produce enough power to deliver adequate performance, and pushing the engines harder caused them to fail. Reducing power to improve reliability made performance even more inadequate. In a desperate attempt to salvage the program, Nakajima built two additional prototypes with different engines. These G5N2 variants used Mitsubishi 4 billion Malawian Kwacha's Kasei engines instead of the troublesome Momori power plants. The Kasei was a proven reliable engine that powered the successful G4M Betty bomber and several other Japanese aircraft, boasting a solid reputation for dependability accumulated over thousands of operational hours. However, the Kasei produced only 1,530 horsepower, significantly less than even the derated Momori. With engines producing only 1,530 horsepower, performance became truly dismal. The G5N2 flew even slower than the original variants, climbed even more poorly, and had even less range. The more reliable engines made the aircraft safe to fly but incapable of performing its intended mission. By 1942, the verdict was clear to everyone involved in the program: the G5N Shinsen was a failure. No engine swap, modification, or refinement could overcome its fundamental problems. The aircraft was simply too heavy for any available Japanese engine to propel adequately. The Navy had spent years and enormous resources developing a bomber that could not bomb. The American aircraft they had purchased, studied, and copied had transferred its flaws along with its technology. The Imperial Japanese Army had briefly expressed interest in the G5N as well, recognizing the value of a four-engine bomber. They proposed two variants of the design, the Ki-68 and the Ki-85, which would use different engines and serve Army requirements. A full-scale mock-up of the Ki-85 was constructed in 1942 at considerable expense, but the Army wisely decided not to repeat the Navy's mistakes, opting to cancel its variants without producing a single flying aircraft. The Navy also canceled the bomber program but refused to waste the aircraft entirely. 4 of the 6 G5N prototypes, 2 of the original G5N1 variants with Momori engines and both of the re-engineered G5N2S with Kasei power plants, were converted into long-range transports. These aircraft were redesignated G5N2L and given the name Shinsen Kai, meaning deep mountain modified. The bomb bays were removed or sealed, offensive armament was deleted, and defensive armament was reduced. The crew was cut down to just 6 men, and the aircraft were assigned to the 1021st Kokutai, a naval air transport unit based at Katoriai Air Base. This unit became the sole operator of all 4 surviving Shinsen aircraft. Throughout the remainder of the war, the 4 surviving Shinsen transports flew supply missions across the Japanese Empire, carrying cargo and personnel to bases in Hong Kong, Formosa, Tinian, the Philippines, and the Mariana Islands. Their long-range capabilities, inherited from the DC-4's transcontinental design, made them valuable for reaching distant garrisons that could not be supplied by smaller aircraft. They transported spare parts, medical supplies, and military equipment to isolated outposts. The mighty bomber that was supposed to strike terror into American hearts ended up serving as a cargo plane, becoming a glorified freight hauler. American intelligence eventually detected the G5N's existence through aerial reconnaissance. Photographs taken from high altitude showed the large 4-engine aircraft at Japanese airfields. Intelligence analysts at the Allied Technical Air Intelligence Unit in Australia studied the images carefully, identifying the type as a heavy bomber. Following the naming convention developed by Captain Frank M. Coy Jr. in mid-1942, the aircraft was assigned the Allied code name Liz. Under this system, Japanese bombers and transports received women's names, while fighters received men's names. The irony was that the Allies assigned this code name expecting the G5N to be a dangerous strategic bomber, unaware that Japan had already abandoned that mission years earlier. The attack that American commanders prepared for never came. They did not realize that Japan had already given up on the G5N as a combat aircraft. The threat they prepared for was hollow. The intimidating 4-engine bombers they photographed were actually just transport planes making cargo runs. The Allied intelligence assessment was not wrong, only incomplete. The Liz was indeed designed as a bomber, but it was simply too flawed to serve in that role. Carl Cover, the test pilot who had flown the DC-4E on its maiden flight and taken Orville Wright for a ride over Dayton, did not live to see the end of the war. After America entered the conflict following Pearl Harbor, Cover returned to military service at the request of General Henry Arnold, the commander of Army Air Forces. He was promoted to colonel and assigned to oversee B-29 Superfortress production at Bell Aircraft's factory in Georgia, bringing the same meticulous professionalism to wartime manufacturing that he had demonstrated throughout his test flying career. His contributions to aviation were remarkable. He had piloted the first flights of the DC-1, DC-2, DC-3, DC-4E, and DC-5, essentially flying the birth of modern commercial aviation with his own hands. On November 27, 1944, Carl Cover died at age 51 in a plane crash during a snowstorm near Dayton, Ohio. He did not live to see victory over Japan Day or to learn what had become of the DC-4E he had tested. A street at Long Beach Airport was later named Cover Street in his honor, a modest memorial to a man who contributed enormously to aviation history. None of the 6 G5N aircraft survived the war. The 4 transport conversions flew until they were destroyed, worn out, or scrapped. Japanese records from the final chaotic months of the war are incomplete, and the exact fate of each aircraft is unknown. Some may have been destroyed by American air attacks on Japanese airfields, while others may have been cannibalized for spare parts as the Japanese industrial base collapsed under Allied bombing. By the time Allied forces occupied Japan, no complete G5N remained. The aircraft survives only in photographs, technical drawings, and the memories of those who built and flew it. The Douglas DC-4E prototype was stripped bare by Nakajima's engineers and reduced to components. Whatever remained after extracting all useful information was likely scrapped for materials as Japan's wartime shortages became desperate. The wind tunnel model that had been painted in Japan Airlines colors and displayed as part of the deception may have survived the war, but its current location is unknown. It may sit forgotten in a Japanese museum storeroom, or it may have been destroyed during the firebombing campaigns that devastated Japanese cities in 1945. The full story of the DC-4E and the G5N did not emerge until after Japan's surrender in August 1945. Allied investigators examining Japanese aviation programs discovered documents describing the Shinsen program and its origins. They learned about the purchase of the DC-4E, the fake crash cover story, the reverse engineering effort at Nakajima, and the disappointing results of flight testing. The elaborate deception that had hidden the program from American intelligence before the war was finally revealed. The irony of the situation was profound and instructive. The United States had rejected the DC-4 because it was too complex and expensive for civilian use. Japan had purchased it, hoping to turn American technology against America. Instead, the Japanese inherited all of the DC-4's problems and added new ones of their own. The same fundamental flaws that made the DC-4 a commercial failure ultimately made the G5N a military disaster. Douglas understood the DC-4's flaws because they had lived through the painful development process. They knew which design decisions had caused problems and why. Those decisions had been made, and they understood the alternatives that had been considered and rejected. When they designed the successor aircraft, they could avoid the mistakes they had made before. They could keep what worked and discard what did not. Nakajima had none of this context. They could see what Douglas had built, but they could not see the reasoning behind it. They did not know which features had been chosen reluctantly as compromises. They did not understand which systems had caused endless headaches during development. This knowledge gap proved fatal to the G5N program. When the Momori engines failed to perform as expected, Nakajima lacked the experience to diagnose and fix the problems quickly. Japanese engine development had not yet reached the level of American or British engineering. When the aircraft proved overweight, Nakajima did not understand the cascade of decisions that had led to those weights. When performance fell short of specifications, they could not identify which compromises to make because they did not understand the original design intent well enough to modify it intelligently. Meanwhile, Douglas applied the hard lessons learned from the DC-4 failure to create something better. The redesigned DC-4 that emerged in 1942 was essentially a new aircraft, retaining only the name and the basic concept of a four-engine transport with tricycle landing gear. It was simpler, lighter, and much more practical, using proven Pratt & Whitney R2000 engines. It featured a conventional single vertical tail that simplified construction and eliminated the complex systems that had caused so many problems. The U.S. military designated this new aircraft the C-54 Sky and ordered it in enormous quantities. Over 1,200 aircraft were built during the war, making it one of the most produced four-engine aircraft of the conflict. The C-54 became the backbone of American military air transport, flying cargo and passengers across the Atlantic and Pacific Oceans. President Franklin Roosevelt used a specially modified C-54, nicknamed the Sacred Cow, as his personal transport. After the war, C-54s supported the Berlin airlift, delivering supplies to the blockaded city in one of the greatest humanitarian operations in history. Many C-54s were converted to civilian use and served airlines around the world for decades. The design that failed as the DC-4E succeeded brilliantly in its revised and simplified form. The lessons learned from the DC-4E and the G5N Shinsen extend far beyond aviation history. Technology cannot be stolen complete, the physical artifact is only part of what makes technology work. The knowledge behind it, the hard-won experience that created it, and the institutional wisdom that guides its use are intangible factors that cannot be put in a crate and shipped across the ocean. Japan spent $950,000 to purchase the DC-4E and years reverse engineering it to develop the G5N. They built 6 prototype aircraft, but in the end, they had nothing but 4 cargo planes and a lesson in the limits of technological imitation. Douglas learned from the DC-4E's failure and created one of the most successful transport aircraft in history. In contrast, Japan copied the failure and produced an even greater failure. The G5N Shinsen, meant to cast a shadow across the Pacific, instead became a cautionary tale about the limits of imitation and the importance of understanding one's own technology. If you found this story compelling, please take a moment to like this video. It helps us share more forgotten stories from the Second World War. Subscribe to stay connected with these untold histories. Each one matters, and each one deserves to be remembered. Leave a comment below telling us where you are watching from. Our community spans from Texas to Tasmania, from veterans to history enthusiasts. You are part of something special here. Thank you for watching, and thank you for keeping these stories alive.